Unit 3, Solubility. This unit will always be in water, therefore it must be polar. Quick definition, solute. It is the thing that is in lesser quantity, while the solvent is in greater quantity. Now, for ionic compounds, so an example of which would be magnesium chloride, they would dissolve into the magnesium and chloride ions, and they would be aqueous. And they can conduct electricity because they have charges. While something like carbon 6, H12, oxygen 6 does not dissolve into ions because it is covalent. Therefore, it cannot conduct any electricity. Now, an ion in a solution is called an electrolyte. That is what allows ions to conduct electricity. And covalent solutions are called non-electrolytes because they cannot conduct electricity. Next page. Now, another definition is a saturated solution. A saturated solution is when the solution has absorbed the max amount of the solid, aka the salt, per its volume of solution. The easiest way to recognize a saturated solution visually is via an excess or undissolved solid at the bottom of the container. Saturated solutions are at an equilibrium, but since their rates are equal, we would not be able to notice a visible change. Now, the difference between the rate of dissolving and the rate of precipitation for an unsaturated solution, so a solution that has not absorbed the maximum amount of solid, is that the fact that the forward rate of dissolving is far greater than the rate of precipitation. Now, this was an unsaturated equation for potassium bromide would be potassium bromide solid turned into potassium ion and bromide ion. That is called a dissociation equation, or breaking into ions. Now remember, everything dissolves, but only ionic compounds can dissociate. Now, another difference between saturated and unsaturated equations is the fact that a saturated equation, due to the fact that a saturated solution has to be at an equilibrium, will have arrows going both ways, while an unsaturated equation will only have an arrow going in one direction because it is not at equilibrium. Now, solubility itself is defined as the molarity of a salt at solution. Therefore, solubility can only be used to measure saturated solutions, or again, solutions that are at an equilibrium. Now, every salt dissociates to some extent in water, but every salt has a different solubility in water. The salts that dissociate to a larger extent, aka dissociates into more ions before becoming saturated, are called soluble salts. They will precipitate a lot before, I believe it is, will, no matter what, create a saturated solution of 0.1 molarity before getting saturated. While a low solubility salt dissociate very little, aka there are low concentration of ions. And they don't dissociate very much. No, I believe they have to be. They have to, what is it? Yeah, low solubility salts will become saturated before reaching the 0.1 molarity benchmark. Also, the solubility of things is temperature dependent. So, an increased temperature increases the solubility, and vice versa. Now you can use stoichiometry to calculate the solubility if you're given as long as you can do the dissociation equation. So that should be fairly easy. You got this, Matthias. Now, as we touched on earlier, that is, low solubility salt does not dissociate much before becoming before they reach 0.1 molarity and become saturated. While a soluble salt will, no matter what, produce a solution of at least 0.1 molarity before becoming saturated. Also, low solubility salts will be solid because, well, yeah. Soluble salts, sorry, ignore what I just said. Now, it is possible for soluble salts to not precipitate. Could precipitate, but that would require a solubility to be exceeded, so a lot of the soluble salt would be needed. And vice versa with the low solubility salt. Now, there are two ways you can create a saturated solution for a salt. The first way is the direct method, and that is just by dissolving the salt directly into water until no more of that salt dissolves. And so you would see some of the precipitate at the bottom of the container. Now, the indirect method, the second method, would be you mix two soluble solutions. So each would contain one of the ions you want, and the other would contain something like NO3 2-, aka nitrate. And the other could contain ammonium, as those are guaranteed to be soluble salts. They're soluble with everything. And then, what is it? Yes. Yeah. Now, the formula equation. That will be used in other things. The formula equation is it's a balanced equation. There are going to be no charges. It's going to be completed, and you must balance it. So, coefficients, subscripts, all that jazz. Also, include your states. You will lose marks if you don't include your states. Then the complete ionic equation is anything that's aqueous, you'll split apart into its ions. And that's just it. Now, the net ionic equation is just the ions and molecules that have changed. So if you had 2A plus 3B plus 2C turns into 3B plus 2AC, I just ignore the numbers, then all you would include would be the 2A plus 2C equals 2AC. Now, let's say you wanted to precipitate a solution. The way you'd write this out is you would add X as X plus thing that makes it soluble to precipitate as X, Y, and then you filter that out. Then you'd add A as a thing that makes it precipitate. Well, no, thing that makes it soluble. Precipitate out. B as well, which is your target, as A, B, and then you filter that out, and then you're golden because you've gotten your stuff out, and then you'll do the same thing for stuff out. Now, yeah. A saturated solution is at equilibrium because the rate of dissolving equals the rate of precipitation. Remember that. That's important. And since an equilibrium exists, we can work with an equilibrium constant, a KEQ. But since to make it so that way we don't confuse them, we will write it as a KSP. Now the KSP of a solution is, unlike the KEQ, is just your products. So your product times your product. There's no division. Because since it's a solid, we don't deal with it. The SP in KSP stands for solubility product. Kind of makes sense. So yeah, this is a very simple thing. Shouldn't be too hard. Now, a soluble salt will have a large KSP constant because they dissociate a lot, aka there's a very high concentration of the resulting ions. While the low solubility salts don't, low solubility salts would have a very small KSP because they don't dissociate a lot. Therefore, there's less ions. Therefore, the KSP is lower. Yeah. Calculate. Now, I will cover the questions in a different video because that's something I can't really explain by myself. Yep. Now, if you wanted to alter the solubility of a salt, what you could do is, what is it? That's right. Describe what I just said. Yeah, stuff. The equivalent. Okay, so a saturated solution equations, so solid on the left, ions on the right, are simply equilibrium equations. In the equilibrium unit, we studied how concentration changes cause a shift. So in the example, they have silver chloride solid is in equilibrium with silver ion aqueous plus chloride ion. Now, if the amount of silver, well, the concentration of silver was increased, it would shift the entire equilibrium to the left because the Chatellier's principle. Therefore, it would the amount of silver chloride solid would increase, and since the solubility of something is just how much it can take before its precipitate forms, the solubility would go down, and vice versa. So if we decreased the concentration of our silver, then that means the silver chloride would decrease, so that way there's more silver, and thus the solubility would increase. Yeah. And that is solubility.